Hi Bobcats! In this video we're going to continue drawing Lewis dot structures. This time around we'll have some more complicated cases where we have to make double and triple bonds. Our objective is to practice drawing more Lewis dot structures. The first compound that we're going to draw is oxygen. Well, I guess that's a molecule, it's an element, not a compound. Oxygen is in group number 16, so each oxygen atom is going to bring 6 valence electrons, and there are 2 of them, so we'll take 2 times 6, which gives us 12 for the number of valence electrons. When there are only 2 elements, it's kind of silly to say that one's a center atom and the other is an outside atom. We'll just draw 2 oxygens side by side, and we'll start by putting an octet on one of them. So there's 4, 6, 8, and then the leftovers will go on the other atom, 10 and 12. Notice that when I put all 12 electrons into the structure, we have a problem. The oxygen on the right-hand side only has 6 electrons drawn around it. It does not have a full octet. So here's how we're going to solve that problem. We are going to take one of the lone pairs from the oxygen that already has an octet, so the left-hand oxygen, and we are going to slide it into the middle to be a bonding pair. Now, when we do that, the electron pair that we're moving still gets to count towards the octet of the left-hand oxygen, but now we can count it for the right-hand oxygen as well. So now redrawing this, we left 2 lone pairs on that left-hand oxygen alone, but now we have 2 shared pairs, or a double bond, and now we have 2 lone pairs on the right-hand atom. So if you look closely at this, the left-hand oxygen has an octet because there are 8 electrons associated with it. Shared pairs get associated with it. And then if you look at the right-hand oxygen, it has 8 electrons as well. When we start drawing a lot of these electrons in one spot, like we're showing here at the double bond, sometimes it's hard to distinguish them. So there's another way that we can draw the structure where we show the lines instead of the dots. And so these 2 structures are equivalent. 2 lines represent the same number of electrons as 4 dots. The element nitrogen also forms a molecule. Nitrogen's in group 15. We have 2 nitrogen atoms. Since they're in group 15, they have 5 valence electrons. So this time around, we're going to have 10 valence electrons to place into our structure. So I'll start by drawing the 2 nitrogens side by side. I'm going to place a bond, and then I'll put an octet on one of the atoms. That uses up 8 of the 10 electrons, and so I'll put the extra pair on the other atom. We really do have a problem with that right-hand atom because it only has 4 valence or 4 electrons shown in the structure. So what we're going to do is take a lone pair off of the left-hand nitrogen and slide it in to be a bonding pair. That will increase the number of electrons on the right-hand atom to 6. And it leaves the number for the left-hand atom at 8. But we still need more for the right-hand atom, so we're going to take another lone pair and slide it over to be a bonding pair also. So cleaning that up, we're going to have a nitrogen atom with a lone pair, and then we're going to share 3 pairs of electrons with its neighbor, and it still has 1 lone pair on it. The other way that we will draw this kind of structure is with 3 lines in place of the 6 dots. So each line represents 1 bond or 2 electrons. And so nitrogen ends up with a triple bond. Ethane belongs to the alkane family. Let's first add up its valence electrons. We have 2 carbons, and since carbon's in group 14, each one brings 4 valence electrons. We have 6 hydrogens, and hydrogen's in group 1, so it brings 6. So 6 plus 8 gives us 14 electrons we will place in the structure. For the backbone of ethane, well, all of the alkanes have a chain of carbon atoms as their backbone. And then just as a guideline, carbon wants to form 4 bonds, and so we'll get the rest of the bonds by placing hydrogens, and carbon will make a bond with these hydrogen atoms. So the backbone of ethane looks something like this. When we go to place those 14 electrons into this structure, we need to start by bonding all the atoms. So we'll stick the 2 carbons together, that's 2, then we'll start sticking each of the hydrogens to the carbons. That's 4, 6, 8, 10, 12, 14. So just making all of those bonds eats up all 14 electrons. Usually when you see ethane drawn, though, we do it without the dots. We just have lines for each of the bonds. So a structure more like what I'm drawing now is what we typically see for the organic molecules. Ethylene is a compound that's very closely related to ethane, the molecule we just drew. It is not an alkane because it doesn't have enough hydrogens. It has twice as many hydrogens as carbons, not 2n plus 2. So let's first add up the valence electrons, then let's figure out the backbone and draw the structure. So we have 2 carbons, and carbon's group 14, so it has 4 valence electrons. And we have 4 hydrogens, and hydrogen's in group 1, so it has 1 valence electron. So this gives us a grand total of, let's see, 2 times 4 is 8, plus another 4 gives us 12 valence electrons. Just like ethane, ethylene has a chain of carbon atoms as its backbone. So we've got carbon and carbon. But now, since there are only 4 hydrogens, each ethane will have 2 hydrogens attached to it instead of 3. Now, when we go to create this structure, let's bond all the atoms together first. So we'll have 2, 4, 6, 8, 10, and we still have 2 electrons to place somewhere. If you'll check out both of the carbons, they each have 6 electrons around them, not 8. So if I put the extra pair of electrons in between the 2 as a shared pair, we'll end up with an octet on both carbons. And remember, hydrogen only wants a duet, so hydrogen is good in this structure. Now, normally when we draw these organic molecules, we just draw the lines instead of the dots for the bonds. So a more commonly encountered version of the Lewis structure for ethylene is something like this, with the lines instead of the dots. For our last example, we're going to look at acetylene. Acetylene is in the same family as ethane and ethylene, but it's lost yet another 2 hydrogens. So when we count valence electrons, there are 2 carbons, and carbon's in group 14, so it'll have 4 valence electrons. And then we have 2 hydrogens, each bringing 1 valence electron, so that gives us a grand total of 10 valence electrons to place in the structure. Once again, we have 2 carbons side by side as the backbone, but now there's only an additional 2 hydrogens, so we'll put 1 hydrogen on each carbon atom. When we start to place the 10 electrons into the Lewis structure, we'll want to bond all of the atoms together first. So there's 2, 4, 6. And once we put those 6 electrons in, both of the hydrogens are good because they only want a duet, but both of the carbons are way short. The carbons only have 4 electrons associated with them, and they need 8, but I only have a total of 4 more electrons that I can place. So we're going to want to share those 4 electrons with both carbons. So we'll go ahead and make a triple bond. So by placing those 4 extra electrons as a second and a third bond, we're able to satisfy the octet on the carbons. So if can't see that one. Hang on, I got to change my pen color again. If we're looking at the left-hand carbon, it has an octet, and if we look at the right-hand carbon, it has an octet of electrons as well. And once again, usually with the organic molecules, they are not drawn this way. They are drawn with the lines instead of the dots. And so this is a much more common version of the structure for acetylene. Acetylene is used in welding. Oxyacetylene welding is one of the forms that you'll find. This is one that has the gas cylinders. So where are we going next now that we know how to draw the Lewis dot structures? Well, the Lewis dot structures are a great representation of the structure of molecules in 2 dimensions. They will show us what atom is connected to what other atom, because if you can draw a good Lewis dot structure with everybody following the octet rule, it's a pretty good chance that's really how the molecule works. But we need to move from 2 dimensions into 3 dimensions because real molecules exist in a 3-dimensional world, and it turns out that the 3-dimensional shape of molecules can be very important for the reactivity of the molecules, particularly in biological systems like your body. And so we are going to look at something known as VSEPR structures. VSEPR stands for valence shell electron pair repulsion. It's a theory that more or less just says electrons repel each other. So these bonding electrons are going to spread out in 3 dimensions to get as far away from one another as they possibly can. That will determine the shape of the molecule, and that will determine all sorts of wonderful things about the molecule's chemical behavior. Our objective was to practice drawing Lewis dot structures of compounds. We added a series of organic molecules, ethane, ethylene, and acetylene. They required multiple bonds, and we also looked at a couple of elements, nitrogen and oxygen, that fell short of the octet, so we had to move lone pairs to be shared pairs to make sure that every atom had an octet.